Today I'm going to be showing you the world's most dangerous candle. It can't be blown out, it's attracted to you, and it can even melt steel. This fire is way hotter than regular fire. For example, let me show you comparing it to a regular flame here. I have my lighter and my plasma flame here. You can see that first you can't blow it out. If I blow on it, it blows out the lighter but not the plasma flame. And second, watch how fast it can light things on fire when you stick it in it, compared to a normal flame. So here's a regular flame. Takes a while to light it. Okay, now let's do this one. The reason it's so hot is because you're tearing off electrons from the gas molecules around it. In fact, it's so hot that if I just grab a small piece of steel and put it in the flame, it melts it. Whoa, look at these sparks flying. It's like I'm welding. But this is different than an electrical arc welder because it's not using a high current. It's using a very small amount of current, but a very high frequency alternating high voltage. Because of this high frequency alternating current, you saw that it could trip the AFCI breakers in my house, but that also means that you can light regular things by just holding it in your hand. For example, here's a tube of helium, and when I bring it close, it just lights it up. The electromagnetic waves that the Tesla coil is sending off are high enough to rip the electrons off of the helium atoms, but then when they recombine, they emit light. Here's one with neon. Or you can even just use an LED as well. One question that I had when watching this operate is, why does it look like regular fire? It's a little bit different color than regular fire. It's more whitish, but it's definitely more orange than other Tesla coils that I've operated. For example, here's a different Tesla coil that uses a lower frequency. And in this one, you can see that the plasma that's produced at the top of it is much more in the purplish blue range of light. Usually when you look up what the color of air plasma is, you'll find that it's in the blue or purple range. But the true color is much more variable. That's because air has so many things in it regularly, like water molecules, nitrogen molecules, and oxygen molecules, and there's also CO2, argon, and other things. Because it has so many different species that are actually quite reactive, there's a lot of different ranges of ions that you can get. And depending on how hot your plasma gets, you'll get different frequencies of light coming off of it at different ranges. When you get air extremely hot, it actually enters more of the white range. It's emitting a much broader range of frequencies, so it appears white. But when it's a little bit colder, that's when it emits those characteristic blue sparks that you see on a static discharge when you touch something. You can see that when the sparks are just spreading out in one direction, it appears more bluish and purple. But if I can actually concentrate it into one area, you can see that it actually looks more whitish. This looks much more like the flame that I was producing with the ultra high frequency Tesla coil. And you can also see when I blow on the plasma, it looks more like sparks rather than a regular fire. No matter where I put it, even in its own isolated circuit, it was still blowing the breakers in my house. But I noticed that the only breakers that it was tripping were the AFCI breakers. These are breakers that for safety reasons are required to be put in every bedroom and bathroom in your house. What these breakers do is they're able to distinguish between a spark that's going to cause a fire and a regular spark that occurs in everyday use in your house. For example, sometimes when you turn on a light switch in your house, when the connector comes to connect, there can be a small little spark that occurs there. And you don't want your breaker to trip every time there's a spark like that. But what these AFCI breakers do is they're able to tell the difference between a normal spark like this and a spark that stays for a long amount of time that could start a fire. What it does is it trips when there's a high frequency current going through it. These high frequency currents are associated when you have arcing events at your house. So for example, if you have a hot wire and a neutral wire that suddenly touch or get close together, an arc occurs there, and those arcs typically happen at a high frequency range. What's happening when I turn on my high frequency Tesla coil is it's actually inducing a high frequency current in the wires in my house. So even though I'm not even directly connected to the circuit, it's still sending out that electromagnetic impulse, and it's alternating the current a little tiny bit in the wires in my house, and that's enough to trip the breakers. So this is kind of cool. It actually sends out this electromagnetic pulse that trips all the AFCI breakers in your house, even though you're not connected to the circuit. So that actually means that you could walk by your friend's house with one of these on its own circuit and turn it on and trip the breakers in their house. But don't do that. I did find one way that I could get it to work in my house without tripping the breakers, and that's when I put it directly on my concrete floor. The concrete floor must be able to absorb enough of those electromagnetic waves coming out that it doesn't trip the breaker or doesn't induce enough current to trip the breaker. And thanks for watching another episode of the Action Lab. I hope you enjoyed it, and thanks for watching, and I'll see you next time.